Hello, my dear. I'm inviting you to the lecture on astronomy. And today we have lecture number 19, Modern Cosmology. For beginning, let's look at your thumb. The matter in your body was present in the fiery beginning of the universe. Cosmology, the study of the universe as a whole, can tell you where your matter came from, and it can tell you where your matter is going. Cosmology is a mind-bendingly weird subject, and you can enjoy it for its strange ideas. It is fun to think about space stretching like a rubber sheet, invisible energy pushing the universe to expand faster and faster, and the origin of vast walls of galaxy clusters. Notice that this is better than speculation. It is all supported by evidence. So cosmology, however strange it may seem, is a serious and logical attempt to understand the structure and evolution of the entire universe. This module will help you climb the cosmology pyramid, as you can see on this slide, one step at a time. You already have some ideas about what the universe is like. Start with those, test them against observations, and also compare them with scientific theory. Step by step, you can build a modern understanding of cosmology. Each step in the pyramid is small, but it leads to some astonishing insight into how the universe works and how you came to be a part of it. Most people have an impression of the universe as a vast ocean of space filled with stars and galaxies. But as you begin exploring the universe, you need to become aware of your expectations so they do not mislead you. The first step is to deal with an expectation so obvious that most people, for the sake of a quiet life, don't think about it. In your daily life, you are accustomed to boundaries. Look, rooms have walls, athletic fields have boundary lines, countries have borders, oceans have shores, right? It is natural to think of the universe also as having an edge, but that idea can't be right. If the universe had an edge, imagine going to that edge. What would you find there? A wall of some type? Or maybe great empty space? Or nothing? Even a child can ask, if there is an edge of the universe, what's beyond it? A true edge would have to be more than just an end of the distribution of matter. It would have to be an end of space itself. But then, what would happen if you try to reach past or move past that edge? An edge of the universe violates common sense, and modern observation, which you will study a bit later in this lecture, indicate that the universe could be infinite and would therefore have no edge. Perhaps even more important, if the universe has no edge, then it cannot have a center. You find the center of things. Look, pizza, football field, oceans, galaxies, by referring to their edges, right? If the universe has no edge, then it cannot have a center, right? It is a common misconception to imagine that the universe has a center. But as you just realized, that it is impossible. As you study cosmology, you should take care to avoid thinking that there is a center of the universe. Okay? Of course, you have noticed that the night sky is dark. That is an important observation because you may be surprised to learn seemingly reasonable assumptions about the universe that can lead to the conclusion that the night sky actually should glow blindly. This conflict between observation and theory is called Olber's paradox, after Heinrich Olbers, a physician and astronomer who publicized the problem in 1826. Problem or question might be a more accurate word than paradox. Olbers was not the first person to pose this question. The problem of the dark night sky was first discussed by Thomas Diggers in 1576 and Edmund Halley in 1721. Olbers gets the credit though through an accident of scholarship on the part of modern scientists who were not aware of the earlier discussion. The point made by Olbers seems simple. Suppose you assume, as did most scientists in Olbers' time, what the universe is infinite in size, infinite in age, static, a fancy word for unchanging overall. Okay? And filled with stars. If you look in any direction, your line of sight must eventually run into the surface of stars. The clumping of stars into galaxies and galaxies into clusters can be shown mathematically to make no difference. Let's look at this figure, please, which uses the analogy of lines of sight in a forest. When you are deep in a forest, every line of sight ends at a tree trunk, and you cannot see out of the forest. Are you agree with me? By analogy to view from inside a forest, every line of sight from Earth into space should eventually end at the surface of a star. Of course, the more distant stars would be fainter the nearby stars because of the inverse square law. Remember this, okay? However, the farther you look into space, the larger the volume you are viewing, and the more stars are included. The two effects cancel out. The result should be that the entire sky should be as bright as the surface of an average star, like suns crowded, shoulder to shoulder, covering the sky from horizon to horizon. It should not get dark at night. Astronomers and physicists who study cosmology called cosmologists and now believe they understand why the sky is dark. Olber's paradox makes an incorrect prediction because it is based on incorrect assumptions. The universe may be infinite in size, but it is neither infinitely old, and nor static. The essence of modern cosmology's answer to Olber's question was suggested first by Edgar Allan Poe in 1848. Poe proposed that the night sky is dark because the universe is not infinitely old, but came into existence at some finite time in the past. The more distant stars are so far away that light from them has not yet reached our planet Earth. That is, if you look far enough away, the look back time approaches the age of the universe, and you see to a time before the first stars began to shine. The night sky is dark because the universe had a beginning. You can now answer Olber's question and understand why the night sky is dark by revising your original assumptions about the universe. The answer to Olber's question is a powerful idea because it clearly illustrates the difference between the universe and the observable universe. The universe is everything that exists, and it could be infinite. The observable universe, in contrast, is the part, maybe a very small part, that you can see from Earth using the most powerful telescope. You will learn later in this module about evidence that the universe is around 14 billion years old. That means you can't observe objects farther away than a look back time of around 14 billion years. Do not confuse the observable universe, which is finite, with the universe as a whole, which might be infinite. There is a common misconception that the universe is unchanging overall and not evolving. In the next section, you will discover that the universe is actually changing. Observations reveal an expanding universe. In 1929, Edwin Hubble published his discovery that the sizes of galaxy redshift are proportional to galaxies' distance. Nearby galaxies have small redshift, and more distant galaxies have large redshift. You learned this as the Hubble law several classes ago. I hope you remembered, right? When you used it to estimate the distances to galaxies. Those galaxy redshifts, interpreted as Doppler shift, implies that galaxies are receding from each other and that the universe is expanding. And this figure shows spectra of galaxies in galaxy clusters at various distances. The Virgo cluster is relatively nearby, and its redshift is small. The Hydra cluster is very distant, and its redshift is so large that the two dark spectral lines formed by ionized calcium are shifted from near the ultraviolet wavelengths well into the visible part of the spectrum. The expansion of the universe does not imply that Earth has a special location. To see why, look at this figure, which shows an analogy to baking raisin bread. As the dough rises, it pushes the raisin away from each other at speeds That's the proportional to the distance, right? Two reasons that were originally close to each other are pushed apart slowly. But two reasons that were far apart, having more tau between them, are pushed apart faster. If bacterial astronomers lived on a resin in your resin bread, they could observe the redshift of the other resins and derive a bacterial Hubble law. They would conclude that their universe was expanding uniformly. It does not matter which resin the bacterial astronomers lived on. They would get the same Hubble law. No resin has a special viewpoint. Similarly, astronomers in any galaxy will see the same law of expectation. No galaxy has a special viewpoint. When you look at this slide, you see the edge of the law of resin breadth, and you can identify a center of the law. The resin bread analogy to the universe stops working when you consider the crust, the edge of the bread. Remember that the universe cannot have an edge of the center, right? So there is no center of the expansion. The resin bread analogy is used, but also, as you can see, imperfect. Let's touch another subtopic, the Big Bang theory. And now you are ready to take a historic step up the cosmology pyramid. The expansion of the universe led cosmologists to conclude that the universe must have begun with an event of cosmic intensity. Imagine you have a video of the expanding universe and run it backward. You would see the galaxies moving toward each other. There is no center to the expansion of the universe. So you would not see galaxies approaching a single spot. Thus, you would see the distances between all galaxies decreasing. Eventually, as your video ran back toward the beginning, galaxies would begin to merge. If you run the video far enough back, you would see the matter and energy of the universe compressed in a high density, high temperature state. The expanding universe must have begun from this moment of extreme condition, which cosmologists call the Big Bang. How long ago did the universe begin? You can estimate the age of the universe with a simple calculation. If you need to drive a city, say 100 miles away, and you can travel 50 miles per hour, you divide distance by rate of travel and long the travel time, right? In this example, it gets us 2 hours. Correct. To find the edge of universe, you can divide the distance between two galaxies by the speed with which they are moving away from each other and find out how long they have taken to reach their present separation. The time you calculate by this procedure, an estimate of the universe age, is called the Hubble time and is the same no matter which two galaxies you pick. The details of this simple calculation are given in reasoning with numbers at this time. Like, the Hubble time is an estimate of the age of the universe. You will fine-tune your estimate later in this module, but for the moment, you can calculate the basic observations of the universe, especially the recession of the galaxy, requires that the universe began with a Big Bang about 14 billion years ago. The phrase Big Bang was invented by early critics of that theory, and the label gives a misimpression. Do not think of the edge or a center when you think of the Big Bang. It is a very common misconception that the Big Bang was an explosion and that the galaxies are flying away from the location of that explosion. Instead, try to imagine the entire universe. At the time of the Big Bang, all of the matter that now composes galaxies, stars, people, and atoms was much closer together. But like the universe now, the early universe also had no center and no edge. The Big Bang failed the entire universe, happening everywhere at the same moment as the matter of the universe began to draw apart. A more accurate term might be the big stretch. Also, your imagination tries to visualize the Big Bang as a localized event. You should keep firmly in mind the correct picture that the Big Bang did not occur at a single place, but filled the entire volume of the universe. The matter of which you are made was part of that Big Bang. And so you are inside the remains of that event. And the universe continues to expand around you. You cannot point to any particular place and say, the Big Bang occurred over there. This is a brain straining, or maybe stretching, idea. But you will find more information to help you understand it better later in this module when you study the true nature of space and time. Your instinct also is to think of the Big Bang as an event that happened long ago and can no longer be observed. Like the Gettysburg Address. Amazingly, the look back time makes it possible to observe the Big Bang now directly. The look back time to nearby galaxies is only a few million years. The look back time to more distant galaxies is a large fraction of the age of the universe. Suppose you look between the distant galaxies, seen even farther away and farther back in time. You should be able to detect the hot gas that filled the universe long ago, right after the Big Bang, before the first stars and galaxies formed. The Big Bang occurred everywhere and in whatever direction you look. At great distance, you can see back to the edge when the universe was filled with hot gas, as you can see on this slide. The radiation that comes from such a general distance has a large redshift. The most distant visible objects are faint galaxies and quasars, with redshift around 10. In contrast, the radiation from the hot gas right after the Big Bang has a redshift of about 1,100 times. That means the light emitted as visible and near-infrared light by the hot gas in the early universe arrived at Earth as far infrared, microwave, and even radio waves. You can see it with your eyes, but it can be detected with infrared and radio telescopes. Unlike the Gettysburg Address, the Big Bang can still be observed by the radiation it emitted. That amazing discovery is the subject of the next module. Next module we call the cosmic background radiation. The story of the discovery of radiation from the time of the Big Bang begins in the mid-1960s when the Bell Laboratories physicists Arno Penzias and Robert Wilson were measuring the brightness of the sky at radio wavelength. Their measurement showed a strange extra signal in the system, which they first attributed to the infrared glow from pigeon droplings inside the antenna. Perhaps they would have enjoyed scrapping out the antenna more if they had known they would win the 1978 Physics Nobel Prize for the discovery they were about to make. When the antenna was clean, they again measured the radio brightness of the sky and found the low level noise was still there. The pigeons were innocent, but what was causing the extra signal? The explanation for the noise goes back decades earlier. In 1939, astronomers noticed that spectra of some molecules in the interstellar medium showed that they were based in radiation from a source with a temperature of 2 to 3 Kelvin. In 1948, physicist George Gamow predicted that the cases in the universe right after the Big Bang would have been hot and should have emitted strong black body radiation. A year later, physicists Ralph Alpher and Robert Herman pointed out that the large redshift of the Big Bang material relative to Earth and would lengthen the wavelength of that radiation into the microwave part of the spectrum. In the mid-1960s, Robert Teague at Princeton, USA, concluded the radiation should be just strong enough to detect with newly developed techniques. Teague and his team began building a receiver. When Penzias and Wilson heard of Teague's work, they recognized the mysterious extra signal they had detected as radiation from the Big Bang, the cosmic microwave background radiation. The detection of the background radiation was tremendously exciting, but cosmologists wanted confirmation. Theory predicted that the radiation should have a spectrum like black body radiation, coming from a very cool source. But the critical observation could not be made from the ground because Earth's atmosphere is opaque at the predicted black body peak wavelength. It was not until January 1990 that satellite measurements confirmed that the black background radiation has exactly a black body spectral distribution. Black body spectral distribution at our sun is like this, with an apparent temperature of 2700 plus minus 2 Kelvin, close to the original prediction. It may seem strange that the hot gas of the Big Bang seems to have a temperature of just 2.7 degrees above absolute zero, but recall the tremendous redshift. Observers on Earth receive radiation that has a redshift of about 1100, and that is the wavelength of the photon, about 1100 times longer than when they were emitted. The gas clouds that originally emitted the photons had a temperature of about 3000 Kelvin, and they emitted black body radiation with a lambda maximum about 1000 nanometers. Also, that wavelength is in the near infrared. The gas would also have emitted enough visible light to be seen glowing oranges if there had been a human eye present at the time. The redshift has made the wavelength of the background radiation about 1100 times longer on arrival at Earth than when they were emitted, and so lambda maximum, and you can see all of this part, lambda maximum, lambda maximum, lambda maximum, and lambda maximum, is about 1 million nanometers, or 1 millimeter. That is why the hot gas of the Big Bang seems to be about 2.7 Kelvin. It means 1100 times cooler than it was. The next subtopic, the story of the Big Bang. The first few steps up the cosmology pyramid have not been very difficult. Simple observation of the darkness of the night sky and the redshifts of the galaxies tell you that the universe must have had a beginning. And you have seen that the cosmic microwave background radiation is clear evidence of the Big Bang, that the early universe was hot and dense. Theorists can combine these observations with modern physics to add some details to the story of how the Big Bang occurred. Cosmologists cannot begin this history of the Big Bang at time zero, because no one understands the physics of matter and energy under such extreme conditions. But they can come surprisingly close. If you could visit the universe when it was only 10 millionths of a second old, you would find it filled with high energy photons having a temperature well over 1 trillion Kelvin and a density of 5 times 10 in power 18 kilogram per cubic meter. This is greater than the density of atomic nucleus. When cosmologists say the photons have a given temperature, they mean the photons have the same spectrum as black body radiation emitted by an object of that temperature. Consequently, the photons in the early universe were gamma rays with very short wavelength and therefore very high energy. When cosmologists say that the radiation had a certain density, they refer to Einstein's equation. I hope you remember. Energy proportional mass times speed of light squared. Using that equation, you can express a given amount of radiation energy per volume as if it were matter of a given density. If photons have enough energy, two photons can interact and convert their energy in a pair of particles, a particle of normal matter and a particle of antimatter. When an antimatter particle meets its matching particle of normal matter, imagine, when an antiproton meets a normal proton, for example, the two particles annihilate each other and convert their mass into energy in the form of two gamma rays. In the early universe, the photons were gamma rays and had enough energy to produce proton-antiproton pairs or neutron-antineutron pairs. So, when these particles collided with their antiparticles, they converted their mass back into photons. And thus, the early universe was filled with a dynamic soup of energy flickering from photons into particles and back again. While all this went on, expansion of the universe caused the temperature of the radiation to drop, reducing the energy of the photons. And when the universe was 0.0001 second old, its temperature had fallen to 1012 Kelvin. By that time, the average energy of the radiation photon had fallen below the energy equivalent to the mass of a proton or a neutron. So the gamma rays could no longer produce such heavy particles. Those particles that did exist combined with their antiparticles and quickly converted their mass into photons. All of the protons and neutrons should have been annihilated with their antiparticles. But for reasons that are fully understood, a small excess of normal particles exists. For every billion protons annihilated by antiprotons, one survived with no antiparticles to destroy it. And consequently, you live in a war of normal matter, and antimatter is very rare today. Also, the gamma ray photons, did not have enough energy when the universe was older than about 0.0001 seconds to produce any more protons and neutrons. And they could still produce electrons and anti-electrons called positrons. Okay? So electrons and anti-electrons we call positrons, which are about 1800 times less massive than protons and neutrons. That process continued until the universe was about 1 minute old, at which time the expansion had cooled to point at which there were no remaining radiation photons with enough energy to create electron-positron pairs. Again, most of the electrons and positrons combine to form photons, and only 1 in a billion electrons survive. Cosmologists can calculate, based on the known properties of subatomic particles and the characteristics of the universe, that the protons, neutrons, and electrons, of which our universe is now made, were produced during the first minutes of its history, only that time. The universal soup of hot gas and radiation continued to cool. Radiation photons with high enough energy can break up an atomic nucleus. So, the formation of the stable nucleus could not occur until the universe had cooled enough. By the time the universe was about 2 minutes old, for protons and neutrons could link to form deuterium. Yes, the particles of heavy hydrogen atom, with a being immediately broken apart. By the end of the third minute, further reactions began converting deuterium into helium. Yes, deuterium into helium. Almost no atoms heavier than the helium could be built in the Big Bang. However, because there are no stable nuclei with atomic weight of 5 to 8, so we cannot see it. This one up to 9 to beryllium, from 5 to 8. In this, in units of the hydrogen atoms here. Nuclei of atomic weights 5 and 8 are radioactive and decay almost instantly back into smaller particles. Cosmic element building during the Big Bang had to proceed step by step, as you can see here, like someone holding up a string of stairs, right? The lack of a stable nucleus of atomic weight from 5 to 8 meant there were missing steps in the stairway. And the step-by-step reactions had great difficulty jumping over these gaps, right? Over these gaps during the few minutes of the Big Bang. And as a result, cosmologists can calculate that only a tiny amount of lithium, atomic weight of 7, would have been produced during the Big Bang, and no heavier elements at all. By the time it was 3 minutes old, the universe had become so cool that almost all nuclear reactions had stopped. By the time it was 30 minutes old, the nuclear reactions had ended completely. At that point, about 75% of the mass of the universe was in the form of protons, hydrogen nuclei. The rest was helium nuclei. That composition, that during the first minutes of the universe, is the composition observed now for the oldest star. Formation of elements with atomic weights greater than lithium had to wait for relatively slow cooking nuclear synthesis processes in stars, beginning many millions of years after the Big Bang. At first, the universe was so hot that the gas was totally ionized, and the electrons were not attached to nuclei. The free electrons interacted with photons and so easily that a photon could not travel very far before it encountered an electron and was deflected. The photons interacted continuously with the matter, and the radiation and matter cooled together at a rate fed by the expansion rate of the universe. Into those circumstances, the universe was dominated by the radiation. As the young universe continued to expand and cool, it went through the important changes. First, when the universe reached an age of roughly 50,000 years, the density of energy in the form of photons became less than the density of the gas. Before that time, ordinary matter could not clump together because the intensity of photons smoothed the gas out. As we will learn in the next section, dark matter, which does not interact with photons, could start clumping much earlier. Once a density of the radiation fell below that of ordinary matter, the ordinary matter could begin to draw together under the influence of the gravitational attraction of dark matter to form the clouds that eventually became galaxies. The expansion of the universe spread the particles of the still ionized gas farther and farther apart. As the universe reached the age of about 400,000 years, The second important change began. The free electrons were spread and so far apart that the photons could travel for thousands of parsecs before being deflected by an electron. That is, the universe began to become transparent. At about the same time, the third change happened. As the falling temperature of the universe reached 3000 Kelvin, protons were able to capture and hold free electrons to form neutral hydrogen, a process called recombination. This term, by the way, is a little misleading because the particles had never been together stable before. Combination would be more accurate. As the free electrons were doubled up, the gas finally became almost completely transparent, and the photons could travel through the gas without being deflected. After recombination, also the gas continued to cool, and the photons no longer interacted with the gas, and consequently, the photons retained the black body temperature that the gas had at recombination. Those photons, which started their journey with a black body temperature of 3000 Kelvin, are absorbed now as a cosmic microwave background radiation. Remember that the large red sheet, the expansion of the universe, has stretched the wavelength of the background radiation so that it appears now to have a temperature of about 2.7 Kelvin. Recombination resulted in the gas of the Big Bang being natural, warm, and transparent. As the universe expanded and cooled, the glow from the warm gas faded into infrared wavelength, and the universe entered what cosmologists call the Dark Age. A period lasting about 400 million years until the formation of the first star. During the Dark Age, the universe expanded in dark. The Dark Age ended as the first stars began to form. The gas from which the first stars formed contained almost no metals and was therefore highly transparent. Mathematical models show that stars formed from this metal-poor gas and would have been very massive, very luminous, and very short-lived. That first violent burst of massive star formation produced enough ultraviolet light to begin ionizing the gas, and astronomers now looking back to the most distant visible quasars and galaxies and can see traces of that reionization era in the universe. Reionization marks the end of the Dark Age and the beginning of the age of stars and galaxies in which you live now. Look carefully at this figure. It summarizes the story of the Big Bang from the formation of helium in the first 3 minutes through energy-matter equality, recombination, and finally reionization of the gas. It may seem amazing that mere humans limited to Earth can draw such a diagram. But remember that it is based on evidence and on the best understanding of how matter and energy interact. So from the left to right, from left up, electron-positron annihilation, energy density equals So we have radiation dominance, and after that we have matter dominance. We have recombination and reionization. And we can see these first galaxies. Now we have not long ago from that time. Okay? Let's analyze one of the scientific arguments. How do you know there was a Big Bang? A good scientific argument combines evidence and theory to describe how nature works. And this question calls for a detailed argument. The cosmic microwave background radiation consists of photons emitted by the hot gas of the Big Bang. So when astronomers detect those photons, they are seeing the Big Bang. Of course, all scientific evidence must be interpreted. So you need to understand how the Big Bang would produce radiation all around the sky before you can accept the background radiation as evidence. And first, you must remember that the Big Bang event filled the entire universe with hot, dense gas. The Big Bang didn't happen in a single place. It happened everywhere. At recombination, the expansion of the universe reached the stage where the matter became transparent, and the radiation that had previously been trapped, bouncing between matter particles, and was freed to travel through space. Now, that radiation from the age of recombination arrives from all over the sky. It is all around you because you are part of the Big Bang event. And as you look out into space to great distance, you look back in time and see the hot gas in any direction you look, as right or left, as up or down. You can't see the radiation as visible light because the large red sheet has lengthened and wavelength by a factor of 11,000 or so. But you can detect the radiation as photons with infrared, microwave, and radio wavelength. With this interpretation, the cosmic microwave background radiation is powerful evidence that there was a Big Bang that tells you how the universe began. But your argument includes an important point. Okay? Why do you think the universe cannot have a center or an edge? How do you think? Next lecture, we will be continuing our discussion. And for this moment, I think that's enough. Okay? Any questions or propositions? So, I hope, as usually, you enjoyed this lecture, and I'm looking forward to seeing you next time. Bye.